Hello again, everybody. This is our video solution to problem 3, and hey, a bonus, problem 4 from quiz 7. This is spring 2023, Math 302 at Cal State Fullerton. And in the first of these two problems, we're going to determine whether the following statements are true or false. All right, let's see. A, an integral domain is always a field. All right, so what is an integral domain? Integral domain is the one that tells you that if you have a product that equals 0, then that implies that one of the factors is equal to 0. So this shows up for us, for example, in the integers. But the integers are not a field. All right, what is a field? Well, field, the kind of the two big things, of course, it should be multiplicatively commutative, and then the really important one, you can divide all the time, right? There's an inverse for every non-zero element. So this is false because Z is an integral domain, and Z is not a field. Right? You cannot divide 2, right, or by 2, right? So 2 has no multiplicative inverse. Okay, part B here. A ring is always a ring with identity, since 0 is an element of every ring. So this is one of those confusing bits about the terminology. So in the ring axioms, we always assume that there is some element. We tend to call it 0, but it doesn't have to be called that. But there is some element which is an additive identity, right? That is in the definition of a ring. If you don't have an additive identity, you do not have a ring. But we also have this phrase, ring with identity, right? And that can be confusing because you think it has an identity, it's a ring. But they're never ever talking about the additive identity, because we already know if you have an additive, or if you have a ring, you must have an additive identity. What you may not have when you know you have a ring is a multiplicative identity. And so when you say, I have a ring with identity, you must be talking about the multiplicative identity. So this is false, since, well, how about the ring 2z, right? This is all of the even integers, right? Has no multiplicative identity. All right, the next one, z mod pz is a field for all p in the integers. All right, so this is telling you if it's a field, then again, it should be commutative, right? And that actually is true here, right? Z mod pz, being a quotient of the integers, is commutative under multiplication. But you also need to have inverses for every non-zero element. Now, if p is a prime, then this statement is true. But when p is not a prime, we have a big problem. For example, when p is equal to 6, so we're looking at z mod 6z, 2 times 3 is equal to 0, or congruent to 0 mod 6. And that tells us that 2 and 3 are 0 divisors, and we know that 0 divisors cannot be units. So 2 and 3 are not units. Okay, but that means that z mod pz is not a field, so this is false. Now there's another sort of silly way in which this statement is false, which is that when p is, say, -4, we really aren't even defining, right, this typically. We could, right, we could have. But what if you let p equals 0? Well, now you have z mod 0, and well, okay, that could be z. It's not certainly what we usually talk about when we do the modular language. But of course we could do that, and in which case, hey, z is not a field either. Okay, D, the set 2z greater than or equal to 0. All right, so we're looking at all of the integers, and then we're going to multiply them by 2, right? Or all the non-negative integers, and we'll multiply them by 2. Okay, so this is non-negative, and of course, when we multiply by 2, then we're assuring they become even. So even non-negative integers. This satisfies all of the ring axioms. Ooh, is that true? Well, you got to know your ring axioms, right? Okay, well, let's see. Is there an addition and a multiplication? Sure, you can add two even non-negative integers. You can get an even non-negative integer. You can multiply two, no problem there. Uh, Associativity, yeah, it's just normal addition, right, and multiplication, so you get associativity. Is there an identity under addition? Well, 0 is definitely an even non-negative integer. Okay, fine. What about additive inverses? Okay, so if I have 2, for example, in here, then I would also need -2. Oh, negative, yeah. So this is also false. 2 is an element of this set, and 2 additive inverse, right? We know within all of the integers, this is the additive inverse. -2 is not in 2 z greater than or equal to 0. All right. Okay, so actually, yeah, all these are false. Whoops. All right, now problem 4 says for each false statement you found above, provide an explicit counterexample to the statement. And of course, we've already done that here, right? So each one of these we gave an explicit counterexample. Okay, so there we go. We will see you next time with our solutions to Quiz 8.